Amplifiers are there to provide gain, and gain enhances the strength of signal. Gain usually is frequency dependent. The frequency dependence of gain arises due to the presence of reactive components in the amplifier circuit. Gain dependence characteristic is similar to the frequency characteristic of a band pass filter. In the characteristic of band pass filter, one can see a pass band surrounded by two cutoff frequencies. In the gain characteristic of an amplifier 2, there exists a pass band. Here it is called midband. The midband is characterized by a gain which is maximum and frequency independent, almost frequency independent. This midband is surrounded by two frequencies, one lower cutoff frequency, another upper cutoff frequency. The locations of cutoff frequencies and the distance between them are dependent upon the values of capacitors, the values of resistances and resistors that exist in the circuit, amplifier circuit. They can be adjusted, and the adjustment is also necessary. For example, when we want to use the amplifier with a low pass signal, we have to ensure that lower cutoff frequency is as near to zero as possible. And if we want to amplify a high pass signal, we have to ensure that upper cutoff frequency is as high as possible. And when we want a band pass signal to be amplified, we want the amplifier to amplify a band pass signal. We have to ensure lower cutoff frequency and upper cutoff frequency of the amplifier tallying with the edges of the pass band of the signal, and this can be ensured by adjusting the values of capacitors and resistors in the amplifier circuit in practice. Amplifiers Frequency Response Series on Semiconductor Devices and Circuits, lecture number 6.10. Amplifiers are electronic circuits meant for enhancing the signal strength. The amount of enhancement given to the signal is measured by a parameter gain. In practice, what happens is this gain parameter, it depends upon frequency of the signal. At the lower frequencies, the gain decreases with the decrease in signal frequency, and at higher frequencies the gain decreases with increase in frequency, and in the middle the gain remains somewhat stable, varying very little with Frequency. Gain dependence on frequency is a drawback, a shortcoming. It has to be arrested. It has to be removed. In the present session, the focus is on finding the causes that make the gain dependent on frequency, and also to find possible measures to avoid, to eliminate gain dependence on frequency. Now we move to begin the core session. The frequency characteristic of an amplifier. It may be divided into three regions: low frequency region, high frequency region, mid-band frequency region. The region is same as range. Low frequency range, high frequency range, mid-band frequency range. All these three regions, they are shown in graphical form, in the form of a picture in the diagram given in this slide. General frequency characteristic of arbitrary gain function. Notice A represents gain. It assumes a certain value, maximum value, A max, during certain frequency range. This frequency range is called mid-band. So mid-band is frequency range over which the gain is maximum and independent of frequency. If we come to frequencies below the mid-band, you can see gain is falling with the decrease in frequency. This region where gain falls with the decrease in frequency, this is a low frequency range, low frequency region of the characteristic. Above mid-band, there exists a range or region where gain is falling with increase in frequency. This region is called high frequency range or high frequency region. In low frequency range or region, there is a frequency where gain is 0.707 times maximum gain. Our gain is A max by root 2. This frequency is called FL, lower 3 dB frequency. In a similar manner, one can find a frequency in the high frequency range where gain is again 0.707 times maximum gain. That frequency is usually designated by FH. It is actually upper 3 dB frequency. FL is lower 3 dB frequency, FH is higher 3 dB frequency or upper 3 dB frequency. The distance between FL and FH, it is called bandwidth. This is the frequency range. Bandwidth is the frequency range over which the amplifier works well, performs well. Below FL, above FH, one can see signal undergoes a lot of attenuation. A few points regarding low frequency range, low frequency region or low frequency response of the amplifier. The low frequency region describes the frequency response of amplifiers gain at lower frequencies down to 0. In this region, the gain of the amplifier falls with the decrease in frequency. The characteristic of low frequency region is fall, gain fall with the decrease in frequency. The fall of gain with the decrease in frequency is due to presence of capacitances which are in line or in series with the signal path. Amplifier means several components: electronic components, electrical components, We use intentionally certain capacitors. For example, to couple signal source to the amplifier or to couple the load to the amplifier. Bypass capacitor. These are all capacitors that are used intentionally in the design of amplifier circuits. Unintentionally also certain capacitors come into being into the circuit. For example, junction capacitances of the transistor. They also exist in the circuit. Out of these capacitances or capacitors, some are in line, in series with the signal path. These capacitors or capacitances are responsible for low frequency regions gain decrease with the decrease in frequency. Each one of these capacitances, in line or in series capacitances, forms a high pass circuit with its own 3 dB frequency. All these 3 dB frequencies then decide amplifiers overall 3 dB frequency. The components of input signal above which are passed without much attenuation. Some points regarding high frequency response of the amplifier. The high frequency region gives frequency response of the amplifier at high frequencies up to infinity. In this region, it can be noticed gain decreases with increase in frequency. Gain frequency relation at high frequency region is just opposite to that in low frequency region. Opposite in the sense, here in this region, gain decreases with increase in frequency. There, in a low frequency region, gain decrease happens with the decrease in frequency. In that way, they are opposite. The reason for decrease of gain with increase in frequency lies in the presence of capacitances which are in shunt. Low frequency response is governed by in series capacitors, whereas high frequency response is governed by in shunt capacitors. Each one of these capacitances forms a low pass filter with its own 3 dB frequency. All these 3 dB frequencies then decide the amplifier's overall upper 3 dB frequency. The components of the signal below which are passed without much attenuation. So this is the characteristic. This is FL. This is FH. Frequencies below FH. These frequencies, they are passed without attenuation. Frequencies above FL, they are also passed without attenuation. Frequencies below FL, frequencies above FH, they undergo attenuation. Frequency range over which there is not much attenuation. That range is called bandwidth, as already mentioned. Apart from lower frequency range, upper frequency range, there is another frequency range. It is called mid-frequency range. In between low and high frequency regions, there exists a region called mid-band frequency range, over which the amplification is reasonably constant, relatively high and independent of frequency. Now, after dealing each part of the frequency response characteristics separately, now we focus on the total characteristic. The frequency response of any amplifier assumes a bell curve with a specific lower 3 dB frequency and a specific upper 3 dB frequency. The distance between these two frequencies is 3 dB bandwidth, half power bandwidth. Ideally, lower 3 dB frequency requires to be 0 and upper 3 dB frequency requires to be infinity, but in reality, lower 3 dB frequency is not 0, upper 3 dB frequency is always finite. Here one important point to be kept in mind, bell curve is for a practical amplifier. What about ideal amplifier? How the frequency characteristic of ideal amplifier looks like, we need to know, so that the amplifier on hand, practical amplifier, how it compares with an ideal amplifier, or how far or how near a practical amplifier is to an ideal one. Ideal one is an amplifier for which lower 3 dB frequency is 0, upper 3 dB frequency is infinity. Gain is independent of frequency. That is ideal amplifier. But in practice, lower 3 dB frequency is never 0. Upper 3 dB frequency is never infinite. The lower 3 dB frequency is determined in-line in-series capacitors like coupling capacitors, whereas upper 3 dB frequency is determined by shunt capacitors like junction and stray capacitors. As already mentioned, in-line capacitors or series capacitors, they simulate high-pass circuit or high-pass filter. Each capacitor simulates one high-pass circuit with its own upper 3 dB frequency. Here we consider a simple high-pass filter, high-pass circuit, and its frequency response characteristic. This circuit consists of a capacitor C1 and resistor R1. Output is taken across R1. Input is given to series combination of C1 and R1. A little bit of analysis tells that output by input characteristic, it is 1 over 1 minus J 1 by 2 pi R1 C1 F, frequency dependence of the gain characteristic. So this relation, this expression can be put in a simple form as 1 over 1 minus J FL by F. Here FL is 1 over 2 pi R1 C1, and the magnitude of this particular function, frequency response characteristic, is 1 over square root of 1 plus FL by F whole square. Graphically, one can sketch AHJF. This one, the sketch appears like this. From this sketch, one can see higher frequencies, larger frequencies, they are allowed to pass to the output without much attenuation. Lower frequencies are attenuated heavily, separating lower frequencies and higher frequencies. Attenuated frequencies and unattenuated frequencies, there is a boundary. This boundary is FL. FL indicates lower cutoff frequency. To be precise, it is 3 dB lower cutoff frequency. Reason is for designating it as a 3 dB frequency. At this frequency, the gain falls by 3 dB from its maximum value. The distance between maximum gain and gain at FL is 3 dB. This is 3 dB. In terms of amplitude, gain amplitude at FL is 0.707 times maximum amplitude. Each shunt capacitor in the circuit of the amplifier simulates a low-pass filter with its own cutoff frequency. This cutoff frequency is called upper cutoff frequency, usually designated as FH. A simple circuit of filter LP filter, low pass filter, is shown here in A. Here output is taken across capacitor C2 and input is given across series R2 C2. Analysis. This little bit of manipulation gives us output by input, output voltage by input voltage as function of frequency. This ratio is here designated as ALJF. It can be shown as 1 over 1 plus J2 pi R2 C2F. It can be put in a simplified form, 1 over 1 plus J F by FH. Here FH is upper 3 dB frequency. It depends upon values of resistance and capacitance in the circuit equal to 1 over 2 pi R2 C2. As you can see, ALJF is a complex quantity. Magnitude can be found. It turns out to be 1 over square root of 1 plus F by FH whole square. This is magnitude. When we sketch the magnitude function, we get a graph shown in B. From this graph, one can see that lower frequencies, they are passing to the output side without any attenuation, these frequencies. Whereas higher frequencies, they are being attenuated while traveling through the filter circuit. In between these two, there is a frequency FH. It is called upper 3 dB frequency or higher 3 dB frequency. It is also called half power frequency, upper half power frequency. Some points on series capacitors. As already mentioned, each series capacitor simulates high pass circuit with a lower frequency dependent upon the capacitance and resistor in series. Examples for this type of capacitances are amplifiers, input output coupling capacitors, and in case of CE amplifier, emitter bypass capacitor 2. The capacitance that appears in series in the path of the signal from input to output. Each capacitor simulates a high pass filter. Such capacitors are coupling capacitors. In any amplifier circuit, one can find coupling capacitors. In case of CE amplifier, one can find bypass capacitor too. These are all examples for series capacitors. The reactance of these coupling capacitors at low frequencies becomes very large, dropping a significant portion of AC signal, in effect reducing the amplifier gain. Here, an amplifier circuit is shown, equivalent circuit. We are going to probe how series capacitors, input side and output side, how they are going to influence the performance of the amplifier. First, focus on the input side. Here is Vs, source voltage, Rs, source resistance, C1, coupling capacitor, Ri, input resistance of the amplifier, Vi to Vs ratio. It is not at all a difficult thing to find. This ratio can be determined. It turns out to be omega Ri C1 by square root of 1 plus omega Ri plus Rs to C1 whole square. This expression. It is Vi to Vs ratio. This expression is associated with a cutoff frequency, lower cutoff frequency. It is designated as FL1 here. It is equal to 1 over 2 pi Ri plus Rs C1. Similarly, one can go to output side. Here we have RL, V0, C2, R0, a source, AB, Vi. AB, Vi is voltage equal to input voltage Vi amplified by the gain, voltage gain AV. The ratio V naught to AV VA can be determined, and we can have an expression. That the expression looks like similar to the expression which we have for the ratio VI to Vs. That expression is associated with one frequency. That frequency can be designated as FL2, and it is equal to 1 over 2 pi R0 plus RL C2. So C1 is associated with the lower cutoff frequency. C2 is associated with another lower cutoff frequencies. Ideally, our requirement is lower cutoff frequencies remain at 0 or nearly equal to 0. Then amplifier will be able to amplify all the signals, all the frequencies down to DC, 0 frequency. To make lower cutoff frequencies nearly 0, what we have to do from this expression, FL1, one can see for FL1 to be small, C1 requires to be high. For FL2 to be small, C2 requires to be high. So one has to use large coupling capacitances to couple input to the amplifier and output from the amplifier. This is one observation. Another observation is Ri plus Rs requires to be high, R0 plus RL requires to be high too, to make FL1 and FL2 smaller and smaller. To move further, first one is due to input side capacitor. FL1 is due to input side capacitor. Second one is due to output side capacitor. Now we move to shunt capacitors. Each shunt capacitor simulates a low pass circuit with a upper cutoff frequency dependent upon the capacitance and the resistor in series. Examples for this type of capacitances are transistors, junction capacitance, inter-electrode capacitances, stray capacitances, etc. The reactance of these capacitors at high frequencies becomes very large, dropping a significant portion of the AC signal, in effect reducing the amplifier gain. The feedback capacitors. Here it requires to be mentioned that in addition to series capacitors and shunt capacitors, there exists another type of capacitors too. They connect output to input. They are called feedback capacitors. What do they do? What is their impact on the frequency response of the amplifier? This is one aspect we have to ponder over, consider seriously. Here it is being told that feedback capacitors can be transferred to input and output side using Miller's theorem. They appear in shunt at the input and at the output, and hence they can be treated like any other shunt capacitor. Miller's theorem is helpful to us in converting feedback capacitors into shunt capacitors. Once they are shunt capacitors, they can be dealt with like any other shunt capacitor. Now we consider shunt capacitor at the input side and then at the output side. Here is a shunt capacitor C1 at the input side. Vs is the source voltage, Vi is input voltage to the amplifier. One can find the ratio Vi to Vs. It turns out to be Ri by square root of omega C1 Ri Rs whole square plus Ri plus Rs whole square. It is associated with a cutoff frequency, upper cutoff frequency, 3 dB higher cutoff frequency. It is designated as FH1. Its value is 1 over 2 pi Ri parallel Rs C1. Similarly, there is a capacitor shunting the output C2. This capacitor also, like the capacitor, shunt capacitor on the input side, simulates a low pass circuit associated with a upper 3 dB frequency. That frequency here is designated as FH2. Its value is equal to 1 over 2 pi R0 parallel RL C2. First one is due to input side capacitor, second one is due to output side capacitor. Before moving further, let us look at the expressions of FH1 and FH2 a little bit in probing manner. We require, common requirement is FH1 and FH2 large. They need to be large. Larger values of upper 3 dB frequencies require C1 small, C2 small, Ri parallel Rs small, R0 parallel RL small. So from these expressions, from these observations, we have a tool, we have a way in our hands by which we can alter, we can increase FH values. Now lower and upper 3 dB frequencies of the amplifier. So far we considered lower 3 dB frequencies, upper 3 dB frequencies of filters that are simulated by capacitors that exist in the amplifier circuit. Now our focus is on lower 3 dB frequency and upper 3 dB frequency of the total amplifier complete circuit. Here it is said for the total amplifier complete circuit, lower 3 dB frequency is nearly highest of all the lower 3 dB frequencies. Upper 3 dB frequency is nearly lowest of all the upper 3 dB frequencies. So each capacitor gives rise to its own 3 dB frequency, and from those 3 dB frequencies, by considering all those 3 dB frequencies, lower 3 dB frequency, upper 3 dB frequency of the entire amplifier are determined. Now we come to end of the session. In this session, focus has been on frequency response of the amplifier, lower cutoff frequency, upper cutoff frequency, how their values get affected by series capacitors, shunt capacitors that exist in the circuit, and also how to reduce lower cutoff frequency of the amplifier, how to increase upper cutoff frequency of the amplifier. Hope this session is useful to you. We meet again in another session soon with a new topic.